Hello everyone, today I'm going to show my math functions that I wrote. So why did I write math functions? Well, okay, what am I talking about? Well, I made sine, cosine, arctangent, exp, and log in C. It's all in this file that I just opened up in my terminal. So I got all these functions in here. And okay, so what is going on here? So these are approximations of the corresponding math functions. So this my sine approximates sine, and what it does is it approximates it to 10 to the negative 15 or more. It's actually kind of hard to tell how precise it is because to measure how precise it is, I compared it with the sine function that comes with the compiler, that comes with C, not the compiler, but the standard library, and that sine implementation is only accurate to like 10 to the negative 16 about. So it's not going to really be a good, comparing with that function does not really give you the true precision. I would need a more precise sine function, but that is a lot of work and I don't care. It's good enough. so I made a sine, I made a cosine, I made arctangent, I made exp, which is e to the x, I made log. So how does it work? Well, so this is interesting because it's interesting to me. So these functions are about as precise as the ones that come with C standard library. Obviously the C standard library has all these functions already, so I didn't have to create them, but I did. The reason why I did is because there's a game, open source game, that wanted to not be linked to the C standard library anymore because of something that they're doing with Windows or something. I don't know. So they wanted that, and I saw that in the list of things that they want to implement in the game, and I thought, well, I could make my own sine and cosine and all of that, and that would be fun, and it was fun, and I did it, and it's a part of the game now, which is exciting. But anyway, so these functions are about as efficient or about as precise as the standard library equivalent functions. They're also about as fast, and that is very surprising to me because they are not really optimized. They're kind of optimized. I mean, I'm not just doing a very slow way of calculating sine, cosine, and the rest of them, but I didn't really think that hard about how to implement these or how to implement these fast. I just kind of did it. So how do these functions work? Well, there's always two steps. The first step is called range reduction. What that means is sine can accept any input, any real number input, but it's a periodic function, which means every 2 pi it repeats. So because of that, you really only need to know sine from 0 to 2 pi inputs. And not only that, but you really only need to know sine from 0 to pi over 2 inputs because it kind of repeats itself. Like 0 to pi over 2 is like this, and then it just does the same thing but in reverse, and then it just does the same thing but upside down. And so if you know 0 to pi over 2, you actually know the whole thing, and that's called range reduction. So what you do is in the beginning of the function, takes whatever input it's given. The light is really weird. Takes whatever input is given, range reduces it to 0 to pi over 2, and then it uses a polynomial to calculate that input from 0 to pi over 2, and that polynomial is accurate within 15 to 16 digits in 0 to pi over 2 input range. Where does that polynomial come from? Well, it does not come from Taylor series. It comes from the Remez algorithm, which what it does is it's a numerical method for finding a polynomial that fits data well. But unlike something like least squares, where it tries to minimize the sum of squared error. Remez, however you pronounce it, tries to minimize the maximum error. I don't think it's necessarily absolute or relative error. I think you can choose your error criterion, but whatever criterion you choose, it minimizes that. So minimizes the maximum of that. So that's good. So you can kind of get an idea of when you might want to use one or the other. So least squares would probably be more accurate overall, but the maximum error is larger. If you want to just minimize maximum error, that's when remez makes sense, which is kind of what you want when you're writing a general purpose approximation function, because you want to be able to tell people it's accurate to this amount. And you cannot do that with least, well, you could do that with least squares, but it's always going to be a higher number. So you could say, well, it's very good most of the time, but sometimes it's 10 to the negative 3. Well, that's scary, or maybe it's not. I don't know. It depends on the application. But for a video game, it actually, none of this matters at all, and this whole thing is pointless. But anyway, so each one does range reduction, and then it calculates a polynomial that approximates that function very well. That's how all of them work. The sine and cosine range reduction is pretty simple, but arctan's range reduction is so complicated I do not really understand it. I just kind of understand it enough to code it, but I don't really know what's going on. Somehow I range reduced arctangent from negative infinity to positive infinity all the way to 0 to tangent of pi over 32. Or negative tangent of pi over 32 to tangent of pi over 32. So I don't know how. I mean, I can kind of follow the logic, but I don't know the specifics. It's some complicated math because arctangent is not periodic, so that makes it more complicated to do range reduction. But anyway, exponential function and the logarithmic function are actually very easy to range reduce. So what you do, instead of calculating e to the x, you calculate 2 to the x. And the reason why that's great is because in a computer, your number is stored as something times 2 to the something. Well, in double precision floating point. So it's great because your 2 to the something, what am I trying to say? If you want to calculate 2 to the 3, it's easy because you just put 3 in the 2 to the something area, and then you're done. It's kind of hard to explain, but there's no fancy math, there's no fancy trickery. It's literally just put it in it's just messing with the bits and taking advantage of the way the number is formatted in the computer, and that allows you to do 2 to the x really fast. And then if you can do 2 to the x really fast, e to the x is also very fast because you just multiply x by log base 2 of e. Easy. And log is the same thing, so log base 2 is really fast. So if you just want the natural logarithm, you just do log base 2 multiplied by log base e of 2. Fun fact, I don't know if it's that fun fact, but log base a of b is equal to 1 over log base b of a. That blew my mind. That does not seem like it should be the case. Enough math, enough looking at code. Let's see it run. So if I do make test, it'll build all the tests, it'll run all the tests, and it'll graph all the tests. So we're going to see how these functions look when you graph them. Gosh, my face is looking weird. It's going to show what it looks like graphed, and it's also going to graph the error, and it's going to tell me what the maximum error is for each of these functions. So it says about 10 to the negative 15. It's not exact, but it is what it is. So this is sine, cosine, arctangent, well, the exponential function, the logarithmic function. This is sines, the graph of the error. So it looks like range reduction might add some error. when it's done on larger values. It looks like closer to pi over 2 sine's more accurate. It's similar with cosine, maybe. It's kind of hard to tell. Arctangent, who knows what's going on here. Exponent looks like as the number gets bigger, the range reduction kind of loses some precision. Log, again, who knows what's going on. So anyway, those are the graphs. That's the error. It's not using Taylor series, using Ramez algorithm. It means that a Ramez algorithm creates smaller polynomials than Taylor series for the same precision. And it uses Horner's method to calculate those polynomials. Anyway, now let's go to the game. And as you can see in the game's code are Caleb's math functions, which are the same functions. I made a pull request, he accepted the pull request, it's in the code. And these are the functions that drive the game. And what game is it? Well, it's called Classic Cube, and it's Minecraft Classic. Oh, shoot. It's so loud. So this game is Mario. This game's running my sine and cosine function and the rest of them, and that's kind of crazy. And it's using it for sound and for visuals. So yeah, it's so loud, so I'm gonna quit. That's all I wanted to share and wanted to show. Have a good rest of your day. I'm gonna end this video.